Hello, grade sevens. Welcome to some review on what we've been doing in chapter 10. Let me make sure that my pen is. Here we go. Don't want it too thick. Um, let's do some review. We've been looking at patterns and how we can make some calculations about farther along in patterns and see these relationships that are within patterns. So here I have a bunch of patterns that are started. Now I've said to my grade sevens at least that when there's only two designs in a pattern, it's actually hard to tell if there is a pattern. You usually need at least three to see if this pattern's continuing. Because in each of these cases, as we look, from one step to the other, let's look over here from, we have one dot, and then we have three dots. Maybe that step we can make some assumptions. And today we're going to assume that since they added one dot above and one dot to the side, on the next step they might do the same. So they have that initial one, but now they have two above, and now they have two to the right. However, when you only have two things, it's actually almost impossible to know if that would be the next step, but we're looking at linear patterns here, which means they're going up in a consistent manner. And so since we're looking at linear patterns, we're going to make these assumptions how these continue. And so there was one dot at the top, one dot to the side. We could make that assumption. For this one, let's look at this pattern here now. And there was 1, 2, 3, 4, 5, 6, 7 blocks. Now there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're not by 2. Well, what did they do? They added 2 blocks on at the end. And so if they were going to do that again, we could sort of draw what that would look like. Do 1, 2, 3, 4, 5. Super ugly. And then 1, 2, 3, 4, 5 blocks. And that's sort of what it would look like, the ugly version. And so we just added another 2 blocks on at the end. Okay, so we've been looking at continuing these patterns, and now you could continue to draw these patterns. I'm sure you could all do that. But we've been going sort of another step from here, and we have been making tables of values from these. So let's look back at this first pattern here, and let's look at what table of value we could make. So often we've been looking at these designs and talking about figure numbers. So we could have figure number here. This would be figure number 1, number 2. Sorry, this is so ugly. And number 3. And then we'd be continuing. So let's look at figure number. We're going to compare, make a little table of values comparing our figure number to our number of dots. Okay? And so in our first figure, in the very start of the pattern there was figure number 1, and there was 1 black dot. On the second figure, figure number 2, there were 1, 2, 3 black dots. Figure number 3 had 1, 2, 3, 4, 5 black dots. And now we can start to see the pattern. And it's easy to show this pattern on the table of values as opposed to having to draw it. If there was 4, if we had figure number 4, the next step in the pattern, well, we can look here. We've been going up by 2. I added 2 to get to 3. I added 2 from 3 to get to 5. And so if I added 2 again, I would get to 7. Then we could continue it. Well, if I got to 5, I'd add 2 more, I'd get to 9. If I had figure number 6, I'd add 2 more, I'd be at 11. Okay, and so now we have this pattern, and what we've been trying to figure out is can we find this relationship between these patterns? What if I had this unknown number, a variable n, figure number? What would I have to multiply and add to that figure number to make it equal to the number of dots in that pattern? And so my class, we've been talking about how there's a couple things that you need to look at to figure that out. One of them is how much you are adding each time in your pattern. So in this case, we are adding 2 dots every time. Now, does that mean that I can go n and go plus 2, and that's going to tell me how many dots? Well, no, because figure number 1 plus 2 equals 3, doesn't equal 1. 2 plus 2 equals 4, doesn't equal 3. So n plus 2 doesn't work. But this, how much you are adding each time, that means that for every figure number, as we go up, so if I get to figure number 5, there have been 2 dots added each time. And so I can actually, I'm multiplying whatever you're adding step by step, however much it goes up by, that's actually what we're going to be multiplying n by. So if we're finding the relationship with n, it would be 2n. So 2n, does that work? 2 times 1 for figure number. Well, 2 times 1 is 2, but the number of black dots I have is 1. So that doesn't work. And that's why we need to find the other piece of information. Now, the one way, sorry, I'm just going to make this a bit cleaner again. The one way that you can do that is to go back to figure number 0. If we followed this pattern backwards, and I had a sum number and I had to add 2 to it to get to 1, what number would that be? Well, if I went backwards 2 from 1, that gets me to -1. And whatever figure number, at figure number 0, if you go back to figure number 0, whatever the number in that pattern is here, that's going to be what you're going to need to subtract. Because at the very start, actually even before figure 1, there was actually -1 dots. So 2n minus 1. So now I can look and I can say, okay, well, if there are figure number 3, how many dots are there? Well, times by 2. 2 times by 3 is 6. Minus 1 is 5. So that works for figure number 3. Figure number 4, 2 times 4 is 8. Minus 1 is 7. 2 times 5 is 10. Minus 1 is 9. 2 times 6 is 12. Minus 1 is 11. And so I've been able to find this relationship here between the figure number and the number of dots in the pattern. And now I could say, okay, well, what if we got to figure number, I don't know, figure number, let's say 32. Well, now I could use this relationship in this equation here. Well, that would mean that there would be 2 times by the figure number minus 1 number of dots. So 2 times 32 is 64, minus 1 is 63. So in figure number 32, there would be 63 dots. And this is the pattern that we can find here. Okay, let's erase this and do one other of these patterns. How about, let's do this one. Okay, we're looking at these matchsticks. So if we're going to go to the next step here with these matchsticks, well, the next step in the pattern, we added 3 matchsticks to make 2 squares. And so if we wanted to make 3 squares, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 matchsticks. And now we'd have 3 squares. So now one relationship we can look at here is between the number of squares to number of matchsticks. How many matchsticks does it take to make those squares? Number of matchsticks. Sorry, my writing's so messy on here. Such is life. Okay, so look at the number of squares here to the number of matchsticks. So how about when there was only 1 square? How many matchsticks did we need? Well, we needed 4. I'm actually going to leave space for match if there was 0 squares. We needed 4 matchsticks. If there were 2 squares here, we have 2 squares, but I have 1, 2, 3, 4, 5, 6, 7. So they just had to add these 3 on. So now we have 7 matchsticks, because they only had to have add 3 matchsticks now, because they're sharing this matchstick here for the squares. So you only had to add 3 each time. Okay, and when we get to when there's 3 squares, We can count 1, 2, 3, 4, 5, 6, 7, and add another 3, 8, 9, 10. 10 matchsticks needed to make 3 squares. Now we could continue this on. If you wanted 4 squares, well, you'd need to add another 3 matchsticks, and so there'd be 13. If you had 5 squares, there'd be another 3, and you'd be at 16. So what's this relationship here between the number of squares and the number of matchsticks? Well, again, we can imagine this in a variable and look at this. What if you had, let's say, x. I'm going to draw my x's like that to separate them from multiplication signs. If you had x number of squares, how many matchsticks are you going to need? So we can look again and we can see, okay, well, how much is my pattern going up by? Well, it's going up by 3. I'm adding 3 each time. That means that for every one square that I go up, I'm having to get 3 more matchsticks. So if I went up to 4 squares, I would need 3 matchsticks for every one, so I'd be multiplying by 3. So this number here that you're going up by each time, and this should be the same number. These numbers should all be the same, but that's going to be your multiplier. And so that's going to become 3x. I can tell from that. And now when I look back to the beginning, if I follow this pattern back to what if there was 0 squares? Now you could say, well, if there's 0 squares, there's 0 matchsticks. But let's say this pattern is continuing backwards as well as forwards. It goes both ways. And so if we went 3 matchsticks backwards, we would actually get to there being 1 matchstick left. And this number here tells you what you need to add. Now you can always just do guessing and checking. So once you know your multiplier, which is how much it goes up by each time, you say, okay, well, 1 times 3 is 3, plus 1 would get me to 4. 2 times 3 is 6, plus 1 gets me to 7. 3 times 3 is 9, plus 1 gets me to 10. So you can do a bit of guessing and checking, but you can always go back to figure 0, or if there was 0 of your independent variable, and then you can find what that value is for what you need to add or subtract. And now we get this value and this relationship between the number of squares and how many matchsticks you have. And we can use this relationship to solve for, well, what if we needed to make a design, a pattern that had 14 squares in it? Well, how many matchsticks are we going to need to build that? Well, now we can use this. 14 times by 3. You can do this a bunch of different ways. You could do 3 times, if you're doing it in your head. 3 times 10 is 30, and 3 times 4 is 12, so that's 42. So you have 42, and then you're adding 1 more, so you're going to need 43 matchsticks to make 14 squares. Okay? And so we're each in you, I'm going to challenge you guys. You can maybe look at some of the rest of these patterns and continue them and make them into a table of values and try to find the expression that shows the relationship between the figure number and number of squares, or it could be, number of lines and compared to the number of triangles in the design, or whatever it may be, and find those expressions that find that relationship. Okay, hopefully this is all sort of review. I know I just sort of jumped into it without sort of going back to the very beginning of what we were doing, and I just sort of jumped into this part. Hopefully you remember a bit about doing this and how to find that yourself. Just one other quick thing. I'm just going to go to another page. Is just to go, if you are going from, one thing I've at least gone over with my class, sorry 7-1s if you sort of are doing it a different way, is just how if you have a relationship, so let's say we had the relationship 3x plus 2, that you can make a table of values from that. And I'm actually going to say y is equal to 3x plus 2, because this is how we see it in math a lot. And we can make this table of values of x and y values. X usually goes first in your table of values, either on the left, or you could do it horizontally, and then it would go on top, either way. And so we could say, okay, well, if x is equal to 0, if x was 0, then what would y be equal to? And then we have to substitute 0 in for x. Well, it would be 3 times by 0, which is 0, plus 2. So 0 plus 2 equals 2. And so if x was 0, y would be 2. Whoa. Y would be equal to 2. That makes sense. X is 0, 2. This is our addition that we're doing at the end. That constant. Okay. And now if x was equal to 1, what would y be equal to? Well, if you substituted 1 in for x, 3 times 1 is 3 plus 2 is 5. Okay. You substitute 2 in for x. If x is 2, so x is 2, 3 times 2, this would be 2 now. Substitute it in. 3 times 2 is equal to 6. Remember that when we just have this numerical coefficient right in front of that variable, it means that we're multiplying. So 3 times 2 is 6, plus 2 is 8. If x is 3, 3 times 3 is 9, plus 2 is 11. And now we can see our pattern. Every time x goes up by 1, you add 1 to x. Y is going up by 3 every time. It went up by 3. It went up by 3. And so now, without even substituting into our equation, we could say, well, if it's 4, this is going to jump by another 3 to 14. But again, how much it adds by each time. So since we're adding 3 each time, that tells us what our numerical coefficient is over here. So quick review of some of these rules. Should have done that earlier. The number that you have right in front of your variable that you're multiplying your variable by, you should always put it in front, so it's not x3, it's 3x. That's our numerical coefficient. Numerical coefficient. Such fancy names in math. Our letter, which is representing any number, it could be any of a infinite set of numbers, is our variable, because it varies what it is. And this number here, because it stays the same, we always put it at the end, is our constant. Okay, and we always write it in this order, or we try to as much as we can. Numerical coefficient followed by your variable. So if you're multiplying your variable, you put that numerical coefficient first, 3x, not x3, and your constant goes at the end. Okay. So just some quick review. I will set out a few questions that you guys can do from your textbook, just to review what hopefully you should have already learned. Okay, talk to you later, grade 7s. Have a good one. Oh no, how do I stop recording?